Good morning, everyone. Today we're looking at the last section of the unit, inverse functions. In my opinion, this is a pretty straightforward lesson. The long story short, or the end goal here, is to just understand what inverse functions are, and I'll give you the end game. The end game is that the relationship between two functions that are inverses of each other is their inputs and outputs are just interchange. So think of any basic function or equation like y equals 4x plus 7. You take that, you interchange the x and y. X becomes y becomes x, and then you solve for y and you have the inverse function or equation relative to the original. So let's go through some of the reasons why we get inverse functions. Like, I'm going to give you another example. We'll work through specific problems, and then we are just, from the remainder of the week, as we discussed, just reviewing. Okay, so how about, to help understand inverse functions, let's go back to the example, and this is going to be useful later for a certain mechanism that we use to test inverse functions. This example is going to be helpful. Let's go back to that the computer problem we had, where we had a sale, and the sale was $300 off. So if that's the case, f of x equals x minus 300. That's where x was our, what I'm just going to call regular price. And in this case, f of x is our sale price. So this is a basic function that says, like, whatever a regular price is, let's say like $1,000 or $900, we're going to subtract 300 and we get the sale price. Now let's come up with another function where now we interchange the input and the output. So instead of our regular price being our input now is the sale price, with the same relationship that the sale price is 300 less. Therefore, if I want to go for my sale price, I'm given the sale price originally, I want to get the regular price, I'm going to add 300. So this is going to give a new function, which for right now we're going to call g of x, where x plus 300 is our function, where now x is the sale price. And we have the exact same physical situation, like I said before, or consumer situation or whatever. Sale price is x, and then you have to add 300 to it, and that gives you a regular price. So this is the definition of inverse functions, where you just simply interchange the x and the y, and you have some algebraic relationship between them. There's some patterns in there that we're going to look at. We're also going to be looking at how we can test functions, inverse functions, if two functions are inverses of each other. Now, instead of this g of x notation, we're going to use this new notation for inverse functions, which is called f inverse. It looks like f to the negative 1. It is not. It is the notation where you say the inverse of f or f inverse of x. Either way is fine. And that designates that these two functions are related by interchanging their inputs or outputs. Now, originally I had g of x for x plus 300. I could have, if I wanted to, make x minus 300 g inverse. They're both inverses of each other, and typically we, whatever function we start out with, we talk about the other one being the inverse of it, specifically with that notation, even though they're both inverses of each other. Okay, so first off, let's look at just basics in terms of finding inverse functions. In fact, I'm just going to make this a little bit more challenging. Let's just add a 4 to that. So the process is going to be pretty straightforward. First, instead of f of x, we're going to insert a y there, just so it's easier notationally to deal with solving for this. So, sorry if my handwriting is not the best. I'm using a stylus on the iPad, and sometimes it's not as clean as I want it to be. Okay, so first step you're going to do is just insert y for f of x, and then to find the inverse function, we are going to just take the x and y and interchange them. That's it. Okay, so now we're going to solve for y. So first thing we're going to do is subtract 4 over. When I subtract 4 over, I'm also going to move that x to the right hand side and the y to the left hand side. So I subtract over the 4, and now I have 1/5 y on this side. I'm going to multiply both sides by 5, and that would give us 5 parenthesis x minus 4. And now I'm going to use new notation here. F inverse of x, or inverse notation, distribute the 5, and we get 5x minus 20. That'd be our final answer. I do want to focus in, like, 5x minus 20, 100% perfect. I do want to look at this a little later relative to this initial one, to look at some patterns algebraically between inverse functions. Now let's change this up to like a 6x minus 5, something I want to demonstrate here. So first off, we're just trying to find the inverse, insert y for f of x, interchange the x and y, and then solve for y. Of course, y we want on the left-hand side, so I'm going to move this 6y over. I'm going to add 5 over to the other side. So basically I did 2 steps in once. I added 5 to both sides, and then I just took the left-hand side, the equal sign, and the right-hand side, I just interchange them. And now here we're going to divide by 6. X plus 5 all over 6. Then we have f inverse of x. We just put in this notation for the y like I did on the last problem. And then you are done. Of course, we could divide that up into x over 6 plus 5 over 6, but that's fine when we have it. Okay, so this is the pattern that I want us to see, which you can use to help yourself out. When looking at two functions, to see if they're inverses of each other, just like kind of that, like I said, eyeball check, where you're just like gonna look at it and see, yes, that makes sense. The other way is, this is a mental trick to find an inverse from a function. So what am I trying to say? If we look up here, the order in which things are happening to x, first x is being multiplied by 6, and then after that we're subtracting 5 from it. Look at the inverse function. The first thing we're doing is adding 5, and the last thing we're doing is dividing by 6. Those are the inverse operations of what we have up here. Furthermore, they're going in reverse order. So if the last operation we're doing to x is subtracting 5, the first operation over here is the inverse operation, which is adding 5. If the first operation over here is multiplying by 6, the last operation over here is multiplying by 6. And that works over here, which again, a little more nuanced because we have this parenthesis here. Up here, the first thing we're doing is multiplying by 1/5 or dividing by 5, and the last thing we're doing is multiplying by 5 here, or you can think of it like dividing by 1/5. In here, the last thing we're doing is adding 4, and the first thing we're doing over here is subtracting 4. So you can, we can practice this a little later, but you could try it with your homework as well. It's a way of, seeing the relationship of original function to its inverse, as well as finding the inverse. You go, oh, I'm just going to do the inverse operations in reverse order and write out the function. Okay, so here we get somewhat complex notation, not too bad though if we break it down. This is saying if we have f of f inverse of x is equal to f inverse of f of x equals x. Okay, so we just look at one of these, this right here. F inverse of x, that's a function right here. If you recall from yesterday, we had, or from the other day, composite functions where we took one function and plugged it into the other. What this is saying is, if two functions are inverses of each other, and I take one of them and insert it into the other, into the input, we should get out x. If they are not inverses of each other, we're not going to get out x. Okay, why is that true? So once again, what this is saying is, if you take an inverse function like x plus 300, insert it into x here, into the other function, it would simplify to be x. Well, we could check that. X plus 300, plug it into x, so I'd have x plus 300 minus 300. The 300's cancel, you're left with x. let's do the same here. Let's take this and insert it into there. X minus 300 into there will give you x minus 300 plus 300. The 300s cancel and we're left with x, so it works. Well, let's also use this example to come up with a conceptual understanding of why that works. Okay, so I'm going to write it out here. If I have f of f inverse of x should give us out x. Okay, so in this particular case, f inverse of x, if we're taking x and inserting into f inverse, which we're doing right here, that means x is the sale price. So let's see what happens. I'm taking x, inserting into f inverse, whatever that output is, that becomes the input of f, and the output should be x. Let's see if that works. So if I take the sale price, x, insert it into f inverse, we get out the regular price. That is our f inverse of x. So our f inverse of x, again, is the regular price. Now I'm inserting that into f of x. If I insert the regular price into f of x, we get out the sale price, which again was x in this example. And what does x represent again? The sale price. I think when I'm in person, it's a little easier to describe, but that gives some justification for why f of f inverse of x equals x if two functions are inverses of each other. If they're not inverses of each other, then you do not get out x. And this then gives us a way of determining if two functions are inverses of each other. So what we're going to do is we're going to go f of g of x. You could also write it as f followed by g of x. So outside function is x, which is 3 minus 4, and I'm taking my x there from f of x and inserting g, which is 3 minus x over 4. Excuse me. The 4's cancel. I now have 3. I distribute the negative. If I distribute the negative to both of those, 3's cancel and we're left with x. So we're good so far. Now we're going to go the other way where we take f and insert it into g. So you have my g function, open parentheses for the x, divide by 4, and then we are inserting f, which is 3 minus 4x, distribute the negative, 3's would cancel, we have two negatives turn positive, so we have 4x over 4, the 4's cancel, and we're left with x. What you'll find is if you plug one into the other and you get out x, it's always going to be the same for the other way around. So in your homework, if you just want to make sure you practice enough of these to know that you are confident with determining if two functions are inverses. That's one skill we have in this unit, or this section, along with the other one, just finding the inverse of a function. Okay, so coming to the back side now, we're kind of looking at the relationships and characteristics of an inverse function graphically for the most part here. So my notes, even though this is a PDF off of Google Drive, my notes might be a little out of order relative to yours, so I apologize for that. So in any case, first off, let's start looking at inverse functions graphically and see what we have here. So first I propose to you a parabola. The question is, does it have an inverse function without any restrictions? Meaning we just, the domain for the parabola is negative infinity to infinity, and then that domain for the parabola has to be the range for the inverse function. Well, if we look here, if I have some points to demonstrate 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4. Now this is the function. Now we want to look at the inverse of that. Well, if I do the inverse of that, I would interchange all of the x and y values. So 0, 0 would still be 0, 0. And again, you don't have to draw this. You can if you want to, but I'm just trying to demonstrate. We have here 1, 1 would still be 1, 1. But negative 1, 1 is now 1, negative 1, right? So I'm just interchanging the x and y, flipping these two, and then graphing the coordinates. 4, -2 would be somewhere over here, and then 4, 2 would be over here, and we look, we have a sideways parabola, or a left to right parabola. This one's facing to the right. Another way you can look at that, this is symmetrical to the y-axis, and therefore the inverse, the positive y, note it's about the positive y-axis. This is about the positive x-axis. So now if I look at this right here and ask, is this a function? Well, we just do a vertical line test on it. And we see that it wouldn't pass a vertical line test, and therefore the inverse of a parabola is not a function. It is still an inverse relation, but it's not a function. Okay, so instead of doing one, I just wanted to show you the relationship graphically between two basics of the relationship, but now we can hopefully come up with a method for determining if a function's inverse is a function just by looking at the original function. So here the vertical line test shows us that it's not a function, but if you look at these vertical lines are horizontal lines for the initial function. So if I do if I do a vertical line test on a graph, we're determining if it's a function, which it is. If I want to see if its inverse is a function, we don't want to do a horizontal line because, a vertical line, because a vertical line over here is the same as these horizontal lines. So the horizontal line test, and since this one obviously intercepts the graph in many spots, horizontal line, the inverse is not a function. So horizontal line test determines, I'll just write quickly to kind of speed things up for you or do my best efficiently, determine if a function's inverse relation is a function. And then that gets us to what is called a one-to-one function. If I have a function, let's look at like this right here, just like kind of like a basic cubic function. A basic cubic function, if you look, passes a vertical line test and it passes the horizontal line test. That means that it and its inverse are functions, and therefore you do not have any repeats of outputs like you do for a parabola where you have multiple inputs have the same output. That is a one-to-one function, and we can simply break that down into saying that if f and f inverse exist, you have one-to-one. A function f is one-to-one if f and f inverse exist. And keep in mind there's a difference between having an inverse relation and that inverse relation being a function. Every single equation has an inverse. You just simply interchange the x's and y's, but that doesn't necessarily mean that new relation is a function. This is the way that we test that it is. Okay. So now this part we're looking for find the inverse function of this non-algebraic graph. We just have coordinates. So in this case, first let's just go and list the coordinates. And there was two methods that I gave you in terms of graphing these. One is doing something numerically with the coordinates, or two, trying to physically move the points based on the transformations on the graphically. For an inverse function, I highly suggest that you just use the coordinates. It's very quite simple. If we do that, requires hardly any thinking. Like, all you're doing is interchanging the x's and y's and graphing. So look, if we have the coordinate 3, 4 first. I start at 3, 4. If I reverse, so it's a coordinate 4, 3. I'm literally just going to graph it, 4, 3. Next one is 1, 2, is now 2, 1. Next one is -2, -2, which is still -2, -2. And then we have -4, -3. So if, oh, and then we also have 0, 0. Okay, so if we do this, that was actually quite simple to graph. Now, it may be hard to see what, if we overlaid these, it'd be a little easier to see, but essentially why it's easier to do it that way is because graphically it is a reflection about the y equals x line, which is this line right here. So if I impose this upon this and I drew the y equals x line, I think we definitely see that better. But for now, doing these type problems, I just highly suggest just interchanging the x and y's and graphing them. Okay, have a great day. I will see you all block 2.